Now, the thing about latency is that latency is the kind of things that we're pretty good at measuring. We're used to doing all sorts of performance tests on our code and measuring how long does this take, how long does that take. Bandwidth, on the other hand, somewhat different. It's not the kind of thing that can be measured that directly, at least not by code. Bandwidth ultimately is, if we're talking about a highway, how many cars can go through the highway at a given point in time. Now, the thing about bandwidth, unlike many of the other attributes of computing, is that although it grows, it's grown a whole lot slower than almost everything else that's been happening. So the common standard for bandwidth is gigabit Ethernet. Now the thing is, gigabit Ethernet is more than 15 years old. 10 gigabit Ethernet started being rolled out roughly, let's say, at a broad scale 5 or 6 years ago. Let me start with this question. Who knows what is the bandwidth, how fast their production networks are? Yes? Who knows? I've got 2, 3 hands in a room of 30 plus people, all right? Now, arguably this thing matters. So how much data you can move through the network is going to have severe ramifications on the performance of your system. If it's gigabit Ethernet, if it's 10 gigabit Ethernet, that difference, that it's 10x difference, is going to add up. So, but let's talk about what does that actually give you? Because the thing is, when you say the word gigabit, the average developer does sort of an instantaneous translation. Giga, ooh, that's a lot. So much that I don't need to think about it, hence effectively infinity. But the thing is, first of all, there's no such thing as infinite bandwidth. But let's talk about just gigabit Ethernet to give you a baseline. Gigabit Ethernet, what do you get from that? So first of all, understand, network engineers talk in bits, we developers talk in bytes. All right? They didn't say gigabyte Ethernet, they said gigabit. So gigabit equals 128 megabytes per second. All right? That's raw Ethernet. You put TCP on top of that, you're going to be losing about half. So out of the 128 megabytes per second, you're talking about roughly 60 megabytes per second. Throw in some serialization, regardless of which type of serialization, JSON, protocol buffers, whatever. You're going to be losing arguably another half. The bigger the serialization model that you're using, XML serialization, heaven forbid, obviously you're going to be losing a lot more. Use protocol buffers, you're going to be losing a lot less, but every time you're going to be losing something. So out of the 60 megabytes per second, maybe you're talking about 30 megabytes per second, 25, 40-ish, all right? Now, imagine, that's the highway that you've got. Now, you've got performance problems. What's the solution? I know. Let's put a whole lot more servers on the same exact network. That'll work, right? It's like, oh, I can't get home fast enough because of traffic. What should we do? Let's put 100,000 more cars on the same exact highway. In some cases, adding more servers is not going to help. It's only going to make things worse. So it's important to understand, out of that bandwidth, there are going to be constraints, and the more traffic there is, remember that TCP thing that we talked about over here, TCP packet retransmit? The more traffic there is, the more likelihood there are going to be network level collisions that are going to require these type of retransmissions, which are going to slow things down even more. So when bandwidth becomes a problem, latency also starts to become a bigger and bigger problem. And if latency becomes a big enough problem, then you're back into timeout territory. And if you're in timeout territory, then you've got reliability issues. Right? So it's important to understand how these things connect to each other. Now, again, let's put these things a little bit in a historical context. 15 years ago, gigabit Ethernet comes onto the scene. All right? Around that time, we have processors that are doing a couple billion operations per second. Fast forward 15 years, now everybody's got a supercomputer in their pocket with 8 cores, where each of them can do 1 billion operations per second. All right? The amount of memory that we've got, again, go back 15 years, we used to be very happy if we could get a laptop with 2 to 4 gigabytes of memory. Nowadays, we're complaining that the new MacBook Pro doesn't come with 32 gigabytes of memory. Talk about storage. Amazon comes onto the scene with S3. A gigabyte of storage costs whatever it did, 5 cents. Nowadays, who cares? Nobody uses a gigabyte of storage. Are you joking? We're talking about terabytes and petabytes. We've got this big data thing where we're storing everything all the time forever. Storage is almost free. And during this time frame where almost everything else in computing has done 100x, 1000x, 10,000x, network bandwidth has barely cracked the 10x in terms of broad deployment. So we have less bandwidth, relatively speaking, today compared to the amount of data that we're trying to push around as we did 15 years ago. And that's ended up being true for quite some time, that our demands for moving data around are growing much faster than the bandwidth that we have available to move that data around. There's an old joke in the network engineering world that says, never underestimate the bandwidth of a semi-trailer full of hard drives driving down the highway. Now, trying to get that bit by bit across the network is often a whole lot slower than just loading up a bunch of drives and shipping them across the country. And that's actually a feature that Amazon has provided for some time now. They're like, you want to get your data into the Amazon cloud? Ship us a hard drive. Imagine that killer feature, actually taking a physical piece of metal and shipping that across rather than relying on bandwidth. All right? So again, to understand the context of the world that we're in. Now, that's the problem that we had when we started to talk about ORMs. You start loading up more and more data, this bandwidth starts to become very constrained very quickly. So ultimately, from a bandwidth perspective, we want to load the minimal amount of data possible for every single action that we're doing. But now we're kind of in this damned if you do, damned if you don't scenario, right? From a latency perspective, we want to prefetch everything as much as possible. But from a bandwidth perspective, we want to delay loading things until we're absolutely sure that we need them because we don't really have much bandwidth to go around. And now we're in this between a rock and a hard place scenario of saying, well, which is it? Eagerly fetch everything or lazy load everything? And the resolution to that is if you can't eagerly fetch everything and you can't lazy load everything, we might need to decompose our domain model into multiple smaller, more specific domain models where each of them is designed to handle a specific subset of scenarios. And then each of those domain models can potentially be eagerly fetched. But that there isn't necessarily the ability to hop from one domain model directly to another. So we'll talk more about what it means to use domain models and what the domain model pattern looks like as we get towards the end of the class. But I want you to understand that already from this point at a network level, that there are these forces that are pushing us towards decomposing things more and more. All right? So it's going to take some time for us to get to the point where we're ready and able to find those boundaries. But there's this other thing, there's this other attribute that we can do already today, not a very big difference in terms of design, that can make a very big difference in terms of the bandwidth and the performance of our system. So, talking about time-critical data in separate networks. The thing about networks, notice the plural here. You can have more than one network. It is common to have servers that have more than one network card today. And even on top of the same physical network, you can subdivide that into multiple virtual networks, if you will. So instead of having just one monolithic, the network that handles everything, you can have virtual network A, B, C, however many you want, where in essence you're allocating a certain amount of bandwidth to each one. So you could create a high priority network and a low priority network, and that way you can make sure that even if the lower priority network is maxed out in terms of bandwidth, that your high priority network still has some bandwidth earmarked for it for those high priority requests that come through. Now, the question is, how do we make use of that even if we have these type of networks available to us? So let's say that we had an API, a service layer. Let's just call it something related to customers, okay? That had two methods on it, all right? So we had one of them which was, let's say, generate a report, where we've all seen these type of report APIs that they often take a long time to run, they use up a whole lot of data, and we have some other method on this API that deals with fraud. So let's say it's handles a fraud detected. Okay? Two APIs on the same service layer where if we asked business stakeholders and we said, well, given that two users might invoke these two methods at the same time, which of them is more performance critical? Which of them should we respond to fastest? It's likely that the average business stakeholder would say, I can wait another couple of seconds on the report. Let's make sure that we don't get defrauded here. Now, the thing is that the way that something like this by default would execute, where you're talking about a single service layer deployed monolithically, where monolithically means as just a single API, that it really is first come, first serve. So if user A clicked generate report a millisecond earlier, that's the thing that gets run. If we don't have any other bandwidth left, then fraud detected is just going to have to wait. That's how it works. Now, we could say, well, we've got these high priority network, low priority network. We can ask our network engineers, please, can you, when we make an invocation, can you unbundle the TCP requests and look at the HTTP headers? And if it says HTTP post and it says fraud detected, then can you route that over the high priority network? And if the network engineer laughs in your face, then that's probably the best that you could hope for, because it's not going to happen. Nobody is going to be operating at that level of packets in order to route the logic in your system. Luckily, there's a relatively simple solution to this, given that you've already created that physical decomposition, is that you can decide, maybe this API doesn't need to be one single big API, but we can subdivide it into two sub-APIs where we can have a reporting API where all of the reporting methods are going to be sitting over here. And then we'll have a higher priority API over here for dealing with fraud or other things. And that once we've separated out the APIs, and again, this is a relatively simple repackaging of the API that we already have. Right? We're not necessarily talking about rewriting tons of code or redesigning the interactions. But just by virtue of creating a separately accessible API, then we can configure that this API will be invoked over the high priority network, and this API will be invoked over the lower priority network. That can be done very simply at the level of port mappings. So that way, if the low priority network is already saturated and a user comes in and says generate a report, then that's going to end up waiting at the level of that low priority network. When a user at the same time or slightly after invokes the fraud, because the fraud invocation is going over a separate network, because we've bound that client via the port mappings to that separate API on the separate network, then that invocation can go through. So it's one of those things that if you start analyzing your APIs from the element of, well, what data, what processing is more time critical, which of them has a higher business priority, and you start capturing that in the packaging of your APIs, then you can align that logical business decomposition into physical network decomposition as well, and then get a lot of benefits, again, for the performance critical stuff. The amount of bandwidth that we've got physically is limited. All we've got is 25 to 40 megabytes per second of actual raw business data throughput. The question is, how do we allocate that? And we can decide, we can design our systems in such a way that high priority stuff will actually take priority over the low priority stuff. But in some ways that means that the way that we design our APIs needs to evolve, to not necessarily be so entity-centric and to be more, let's call it, priority-centric. Questions so far? Yes? Mm-hmm. Mm-hmm. Mm-hmm.
Is there a higher reliability?
Right. So in essence, what you're saying is by creating more moving parts, for example, instead of having just one API that is deployed to one server farm as is, we create two or potentially more APIs that get deployed to potentially separate server farms, separate networks. And in essence, that creates more work for the infrastructure team, potentially to the point that we might even need to have more teams as a result of that. So you bring up a very valid point that in essence, we're not making the problem disappear, we're moving it, all right? Now, that's the thing when you're dealing with physics, ultimately, is that you can't really make the problem disappear. What you can do is you can move the problem to a place where you have more leverage, all right? And that was one of the big physics revelations is the concept of a lever to say, where do I have more leverage and where do I have less? And then to take the parts of the problem that suit those areas and to say, here I have greater leverage. Here I can solve more of the problem at a lower cost. Not necessarily the whole problem. So in essence, what we're saying is, well, yes, we have more moving parts in the sense of now we have multiple virtual networks, whereas in the past, we just had one network for everything. The reality is that when we, again, look at the problem as a whole, we say, well, we have a choice. We can build the monolithic type of system, and then in order to solve the performance issues that our users are having around fraud detection taking too long when the system is under load, let's redeploy our entire network. Instead of being on 10 gigabit Ethernet, we'll do a 100 gigabit Ethernet rollout. Thing is, that's very expensive and time consuming and may involve some downtime. Now we can say, yes, ideally we'd want to get to the position where we have so much bandwidth that we don't even have to worry about that anymore. But the reality is, again, because of the business environment that we're operating in, where we're getting more and more data and more users that need to be running more and more complex functionality, all of it in higher and higher rates of real time, it's kind of hard to win that battle of physics under the same model of saying one system, one API, one network, one database. That's where we came from. That's the application thinking. It's everything hosted as one big thing. And yes, if you can get away with that, fabulous, fabulous. But let me start 2 steps earlier. Doing this logical decomposition doesn't require us to deploy it to different networks, right? Once we've subdivided these APIs, we can still say, let's host it on the same network. Let's not do virtual networks. Let's not do any of that. But we have the option. So that if/when those business problems start to come up and the fraud starts to take a back seat to reporting, then at that time we can say, you know, either business people, please give us a budget for a much faster network and we'll do whatever we can to roll that out quickly. Or alternatively, we'll subdivide what we've got. So we'll increase the level of complexity of our deployment environment, and that will solve the problem of the high priority stuff better. So in essence, subdivided things logically gives us options. Designing things monolithically does not give us those options. So we start by creating options for ourselves, and then when the complexity is worth it, when the business isn't able to afford a monolithic solution to those problems, great. We have the ability to use them. Does that answer your question? All right. Yes?
I'm trying to run through this because this is very much an RPC kind of solution, and I'm trying to think of how this would work with a more message passing kind of solution. So and then I would probably have like 3 instances to take commands from a queue, and you could still have that they would be processing 3 report commands and waiting until they get finished before they do get the fraud command. Or you would have one instance that is dedicated to a high priority queue, but then you would still have the problem that the network is actually saturated by all the querying from the reporting instances.
So in a message queuing environment, and again, these are APIs that are fairly messaging friendly to begin with. All right, generate report is the kind of thing that usually can be delivered as a asynchronous type of activity as well as dealing with fraud. But so to your question of how would something like this be handled in a message passing type of environment? And we haven't yet talked about what all the messaging patterns are, but my guess is that some of you have already done some messaging, so I'll give a brief answer now, is that when we move to a messaging model, these types of things become concrete messages in their own right, which to some extent reflects this kind of decomposition to begin with. So as you were saying, a generate report command versus a fraud command. Once we have them identified as separate commands, then we can also route them to different queues, right? They don't all have to go to a single queue. And then once they're going to different queues, then those queues can be hosted on different networks. All right? So again, that's a routing configuration model. Why? Because, again, they have already been identified as separate messages that can then be independently routable. So with RPC, because the method is not the unit of routing, but rather the API that you're binding to is the unit of routing, we need to perform this higher level decomposition. With messaging, that tends to happen more naturally. All right?
So but the solution is to actually configure different queues on different networks.
Correct.
Yeah.
Correct. So once we need it, again, as we were saying before, you don't have to start there. You can start by saying, I'm going to have both of these message types go to a single queue. And then from there you can say, you know what, I'm going to create a separate queue for the fraud so that, as you were describing, that if I have a queue full of report requests, that the fraud doesn't necessarily get stuck behind them. So that already gives me some element of a priority queue concept. And then once I have the separate queue, then I can create that on a separate network as a final step. All right? Other questions?
Is there a way to you have one, say you got the fraud queue,
Mm-hmm.
can you have several processes pulling out the fraud requests processing faster, or do you have to have it one thing pulling out the
Right. So in terms of how do we scale either one of these, regardless of whether it's a queuing-based model or whether it's an RPC-based model, the scalability behavior is something that happens behind the network boundary. All right? So both in the RPC scenario, if I have multiple web servers that are all behind this API and a different set of web servers that are behind this API, all right? Or whether I'm talking about a queue-based model where similarly, this is a queue and I have multiple workers that are feeding off of that queue. In both of those cases, those options are available using some kind of load balancing technology. But again, it's happening behind the network boundary. So with regards to this fallacy, we've solved, in some cases, the more pressing problem, because the network boundary tends to be something that is a lot more limited than, say, the number of servers that we can throw at a problem.